Up until recently, or a couple of years ago, I was rather skeptical when I heard 3D printing in architecture. I had these colleagues that got huge research grants, many collaborators, big machines, robots, and these machines, they made small, ugly, yellow things. Then my colleague Ludger Hofer said, well, you should meet Benjamin. He's in my group. And I met Benjamin, and he opened my eyes for the face of the digital, if you want, showing me his work on the digital grotesque. So happily, Benjamin is now appointed professor for digital building technology at the Institute of Technology and Architecture at the Department of Architecture of ETH, where I'm also based. The research focuses on the development of building technologies based on the close interplay of computational design methods, digital fabrication, and new materials. And this, again, sounds more abstract than what you're actually doing. Benjamin is also present as a lecturer, but also in exhibitions in the realm of the arts. So I'm very happy that you can be here and looking forward to your presentation.
Thank you very much for the invitation, Philip. Thank you very much for the nice introduction. I hope I can show more than little yellow ugly things in this event. I'm very excited about the framing of the event today. Also, matters and memory is also a topic that I can very much relate to with our work. And I titled my talk today, Bits and Bricks. I don't know if you can see it already or if I should. Okay, yeah. Much better like this. Yeah. So I wanted to start with a compressed definition of architecture from Ludwig Mies van der Rohe, master of minimalism. Architecture starts when you carefully put two bricks together. There it begins. And the work of our research group, but also the topic of my talk today, will actually examine how digital technologies can fundamentally question the central components of this definition. So the central components of this definition of an architectural tectonic. So using digital technologies, what would be the future bricks look like? Huh? Are they maybe just grains of sand that we assemble together? Who will in future put these bricks together? Could it be robots on construction sites or other machines? Or where will this happen? But last not least, what means carefully putting them together? Can we use, for example, computational design or other strategies to more carefully design our future built environment? And this next background of our research and moderation very much relates to what we heard before in the fantastic talk of Andrew. Construction industry is really a big place where material is exchanged, harvested, and used. So construction industry consumes over 30% of global materials. Me as an architect, I was very surprised to hear all these numbers, the usage of concrete in the world, for example. And at the current state, there's still a very inefficient use of raw materials in architecture. Like it starts from how we use, in which amounts we use materials in buildings, but also what, of course, happens after the demolition of buildings. And one aspect that maybe was already stronger developed in other industry sectors is the digitization. And in construction, this digitization did not really fully happen yet, and there's a huge potential. If you look at construction sites from today and compare them with the construction sites 100 years ago, you almost see no difference in how things are built. And our goal is to really change that, to enter with strong digitalization into this market, into this economy, allowing new, more diverse architecture and more sustainable building solutions. And the topic of my talk will very much circle around these kind of construction methods. Concrete construction, building with formwork. So you have basically two kinds of architecture. You see in the background also the waste of the formwork, and we are seeking for ways how to reduce that. And one instrument that we are using intensely is the 3D printer, but we don't use the small industry 3D printers that you know maybe from design office for prototyping. from these little yellow ugly components, but we work with some of the largest additive manufacturing machines, like this printer that has a print bed of 4 by 2 by 1 meter. And what is very interesting about these machines, that they are actually composing based on information and raw material and energy elements from scratch, without subtraction, without destroying the material actually that is not needed. But those printers are also very unique. They have a unique resolution. So when you look at the screen, you have maybe a high definition, 2000 by 1000 pixels. With these modern machines, you can inform matter in an unseen resolution per layer, 40,000 by 60,000 pixels. That is more than a usual camera can take as a picture. And you can inform this matter in layers of 0.1 millimeter and print these elements within a day or two. So this is a incredible dimension and opportunity for architecture, also to design in building scale with this unseen amount of resolution of information that you can put into buildings. But one fundamental question is also, how can we as designers address this resolution? How can we harvest this potential? And therefore I will show now examples where we use computational design to differentiate and design buildings and not drawing by hand. And so together with my colleague Michael Hansmeier, we were working on an algorithmic subdivision process that allows us to start from very abstract volumetric shapes and differentiate them over in scales in order to explore actually the potential of this computer-driven generative differentiation of forms. So you see here an algorithmic folding process that folds surfaces over and over in multiple generations. And we use this then to design an architecture, to design, in this case for an exhibition, to design an architecture that basically questions some categories that are usually known for architecture. We fuse structure and ornament together. We create forms that oscillate a little bit between chaos and order. So developing symmetries, but also letting the generative design create more wilderness. And we exhibited this in the context of one first exhibition, the Grotesque project at FRAC Centre Orleans, where we wanted to use these technologies paired with additive manufacturing to highlight how different this way of designing but also to manufacture architecture is in the most radical case. And so you see here the 3D printer in use, a 3D printer that would bring this information in terms of binder onto a bed of loose sand and solidifies material only where needed. After this printing process, you basically work in a kind of archaeology and take out these elements that are swimming into the loose sand, and then you have your final new brick. But what is the radical change in architecture is that producing, for example, printing this backside of our installation is not at all faster than the front of this installation. So for the first time, maybe complexity and the level of information is taken out of this equation, and that offers a lot of opportunities in many aspects in architecture. Just to give you some numbers, in such a process, the development time of the algorithms of the software was 1 year, but we could have this time because we could shift the manufacturing to a single week. But my topic here is really also about how information translate into matter. So you see here generated forms composed out of millions of little facets that are then simulated in a computer and then with almost no loss of information turned into matter, like in this exhibition, the Arabesque Wall in Toronto. And we were talking about the traces of the digital process, and you see here a close-up of this installation, and you see, for example, these little layers, 0.1 millimeter, that are on the size of grains of sand, leaving these traces into the artifacts. And the maybe a bit round corners you see here are not based on the artifacts of the printer, but actually of the resolution of the algorithm that was not able to inform this structure fine enough. And that's what we addressed in the next part of this installation, the Digital Grotesque 2. I will show here fragments of our design model that now allows to not only fold surfaces but also create a porous layers, a depth into the structures. Structures that sometimes remind us of coral, of natural structures that have another topology like a sponge, for example. And what you see here now in this virtual model will then be turned into a stone, into a printed sandstone with these 3D printing machines. This would be a floor plan of such a printed structure. And the assembly, this new way of putting bricks together that are now printed, hollow, 5 millimeter thick on the inside, and display this highly articulated surface, but can be built up just like in a Lego system. And this is now the materialized version of this design, where you can see that, and that was also our intention now, to really reach the limits of what can we fabricate out of stone, things that probably a stonemasoner would not be able to carve out of this material. And here a photo of the exhibition. But so learning how to fabricate complex geometry is not for the sake of complexity, but of course this helps us then in other projects. I will focus here more on our exhibitions, but to really reduce material, because every optimization that we start on shapes, on custom shapes, will lead to higher complexity in design, and can only be affordable by using these digital technologies. For example, at this project where we created an optimized slab which reduces the amount of concrete required in construction over 70% actually. And I'm showing now other dimensions of 3D printing processes, because we are not focusing only on this binder jetting, but we also engrave additional functions into materials. In this case, it's an add-on printing process that can basically add layers of reinforcement onto a given surface. The robot can scan these surfaces and perfectly align exactly the strength where it's needed, or also other functions. Or we start working with recycled materials. So in this case, it's a printing process that starting from the binding component to the powder component can work with materials that you can get completely for free, because this is really a waste product from, for example, stone quarries. And we can then print new bricks out of them. For example, on the left side, you see the recycled print of an optimized brick element with this kind of printing technology. And we are also, as architects, always interested about this interrelation between the process of manufacturing, the process of design, but also what the material inscribes into the object. And here this is a project where we're working with a recycled foam that could act as an insulation material, very similar to lightweight concrete, but it uses no cement at all. Cement is a big CO2 emitter, and can be completely recycled and is based on recycled material. But also in this process of solidification, you see the dynamics of this material, shrinking, expanding, and sinking in terms of gravity. But with computational methods, we can control this process to reach the target shape. Lastly, I wanted to talk about these projects where we focus on concrete printing, so on fabricating concrete components, not with formwork, but completely formwork-free, an idea that actually started to be developed in the 30s already. People without any digital technologies developing machines that can, for the first time, then build concrete structures without any formwork, here in large layers. So what I've shown before, this 0.1 millimeter is here maybe 15, 20 centimeters. And we are taking these ideas and combining with our robotic fabrication laboratory that we have as ETH, which can be seen as a giant 3D printer, where we can really manufacture one-to-one large-scale building elements and start to print concrete. But I also want to show how this research develops. So that was our very beginning. And here you see really the material life. In this process, you have to calibrate the hardening of the material with the robotic control. The layers have to be soft enough to still stick together, but harden slow enough or fast enough to then carry the next one. So what you see here are these aesthetic failures that we are producing in our labs that are also very inspiring, that maybe remind us more of cooking, but actually create an aesthetic that we could also hardly achieve in other ways. But we're working in highly interdisciplinary teams. We're working with material scientists, physical chemistry of building materials, structural engineers, robotic engineers, computer scientists, to then also manage to build up these structures without any formwork in a short amount of time, and also to optimize this pumping mechanism that you saw manually still on the background. So what does it mean to 3D print now these components? We print over 2 kilometers of concrete filament per one of these columns. They are all hollow, so they just have 20 millimeter of concrete used here on the thickness. They don't require any formwork, and they can be built up in 2 hours. And it doesn't matter if we print always the same column or always an individual one, and that is also a big difference and opportunity in architecture. And the design is composed out of a structural optimization on the inside, but also this material-driven ornament on the outside. This is an installation that our students did together with the Origin Foundation in Rome, close to here, where they designed and developed these individual columns as a stage design. And this led to our follow-up project, the White Tower in Moulins, that I will now talk about, which is a follow-up project also of the Red Theater, a place that you really have to visit, which is placed on the Julia Pass, a theater on the maybe the highest theater in this world from the Origin Foundation. And the place of the White Tower will be in Moulins, a village where the Origin Foundation is already highly engaged, and they have shown already that they can move buildings in order to make something new happen in these valleys. And in the center of this village, there will be the place of a white tower, La Torre Alba, that will be entirely composed out of these white concrete printed elements. The research starts with investigating surface structures, investigating also shapes. What can we print without collapsing? Also in other studies, interfaces, you see here the colored extrusion to show what happens between the different layers. Of course, another huge opportunity to add another level of information. Investigating structures that are optimized, that really use less concrete than needed, but also assembly mechanisms that allow us to remove and detach these elements once assembled in order to already think about the deconstruction of this structure before we even construct it. And of course, the topic of a material-driven ornament, an ornament that is not generated by the geometry that is inscribed here, but really about the material flow. And I want to finish with this visualization. You have here now a fly-through through the village Moulins, 3D scanned by our colleagues Andreas Wieser, that shows how this temporary structure will be situated in the core of Moulins. An event tower in the upper part. You will have a stage for performances of different kinds, but the entire tower should also become a spectacle to walk through, to experience this new space that is generated by these technologies. I would like to end my talk with a quote from Henry van der Velde, also around the turn of the century. And I have to say it in German, it's for me a bit difficult to translate this. Denn unser Traum von einem geschmeidigen Material, das unsere Absichten so leicht folgt wie die Sprache unseren Gedanken, wird in Erfüllung gehen. Thank you.
Many thanks, Benjamin, for this beautiful presentation, very inspiring presentation. We have a very short time because we should start the coffee break according to the rules for one question. Yeah.
Thank you very much, Benjamin, for this fantastic presentation. It's very inspiring. The question is very practical, really. How big is the time span when these technologies would be general practice and implemented in the world? Thank you.
That's a good question. Of course, that's quite important for us. We also do collaborate with industry, but you can't give a answer that covers all the different aspects. So I've shown already now a family of different processes, and it very much depends on the process itself, how far they are already in the development and how early they can be adopted. But there are already a lot of additive manufacturing techniques implemented also in the realm of construction, often, for example, in the formwork manufacturing itself, so not the direct printing, but indirect printing. And so the answer would be that it really depends on the manufacturing process. One of the, of course, in construction industry, you have to evaluate how materials behave over time. So there's also a certain aspect that you can't accelerate further, but industry woke up, so there are a lot of big industry partners are aware that there's a lot of potential for new developments and are all open and investing in these technologies.
Is it very expensive, and does it become cheaper?
It is not, I mean, that again also depends a bit on the process, but the idea is, of course, that what I've shown here are all more or less economic solutions. So they would become cheaper, much cheaper if you try to differentiate your geometries in order, for example, to save material, etc. So these are all, I mean, and the robotic machines that I've shown are also not very expensive hardware equipment anymore. So also here, the prices are relatively low. It's surprisingly low if you compare these robotic arms with other machines, for example.
Thank you very much.
Welcome.